Assalamu alaikum dear students. This is our second lecture of real analysis 2. Now we are going to define the concepts of Riemann integral formally, and then we will try to elaborate the idea as we have discussed in lecture 1 with the help of some examples. So let's revise. Definition and existence of the integral. First of all, let AB be a given interval. Of course, you need to have an interval where you want to integrate your function with respect to that closed interval AB by a partition. The idea was to get a partition. You know, partition is in fact the set of points, finite set of points of different points. You mean a finite set of points x0, x1, so on, xn is equal to b, with x0 less than x, lesser equal to x, lesser equal to x2, and so on, lesser equal to xn. Yes, you can write writing lesser equal to is a more general way, because you know that when a is less than b implies a is less or equal to b. Okay, I already have told you that the idea of lesser equal to is less or equal. If you are writing less, then you can write less or equal, because this is the idea. Our idea is actually we are using in defining the union of two sets A and B. You know, if x belongs to A, then you can write x is in A union B, and similarly if x belongs to B, then you can write x in A union B. That's why if this is less or equal, A union B means A or B. So if x is less than y, then you can write x lesser equal to y, but converse is not true. If x is lesser equal to y, you can never say exactly that x is less than y or x is equal to y. So that's why this is the more general way. So in fact we are choosing the numbers in the set, one is lesser than the other and the lesser than the other. So here we are writing in a more general fashion. So that's why there is no problem if you write less or equal, or if you write less, then there is no problem. Okay. So now the second main condition is that suppose f is a bounded function defined on AB. This is very important condition. This is the necessary condition, that function f should be bounded on your interval AB. That's why if function is bounded, you can have its boundedness on subintervals as well. Please listen my last lecture, lecture 1, where we have discussed in detail that you know that if function is bounded on the entire interval AB, then it must be bounded on its subintervals as well. So next we are letting that mi is the sup of fx in the ith interval. This means that m1 is the supremum of the function in, right here 1. This is x0, this is x1. So x0 to x1, this was the first interval, right? So m1 would be the sup in first interval, m2 would be the sup of fx value, sup of values in the second interval, and so forth. Mi is in fact the supremum of your given function in ith interval for each I. Similarly, mi is inf of fx. Why you can suppose these without any hesitation? Because f was bounded on the entire interval, so because it is bounded on subintervals as well, so because in every subinterval you can have its supremum and in its infimum, means that function attains its bounds. Okay. Finally, you are writing UPF. Upper sum of your function corresponding to a partition B is in fact mi delta xi, where delta xi we have assumed that xi minus xi minus 1, this is the base length of your ith interval, because when you are forming rectangles either from upper side or from lower side, this is your base length, interval length, right? So we are assuming this is equal to delta xi. Okay, so mi delta xi is the approximate area, this is not the exact area. Similarly, LPF, this is the lower area than the desired area, which is small mi xi delta xi, as we have already defined in lecture 1. And then if you vary these partition with respect to the set of all partition, and we label that set as stylish P means set of all partitions of AB, then the supremum, since every lower sum is inside the area, I mean we are losing some area corresponding to every partition P for a lower sum, that's why the supremum is in fact the better area. Similarly, for lower sums you are taking supremum, and for upper sums you are taking infimum, and this is called the upper integral, and we write here a bar as a symbol that we are finding sums through upper rectangles. And this symbol, writing bar here near A, is that we are taking sums through lower rectangles. Okay, these were the definition that we have discussed in last lecture. Now further, we can further see. Okay, say you have this is partition set of P1 is the first partition, P2 is the second partition, P3 is the third partition, and you have infinite set of partitions. This is in fact the stylish P. So when you are taking sup of P belong to stylish P of LPF, it means that you are varying this partition P. You have, this is a set of lower sums corresponding to P1, P2. What we can write in a simple way, this is equal to sup of P belong to stylish P. Or now if you write the complete set, this is like this: sup of this set LP1F, LP2F, LP3F, and so on. So instead of writing this set again and again, we like to write P belong to stylish P, where stylish P stands for the set of all partitions of your given interval AB, right, and LPF. So we label this symbol for lower integral. This is A to B fx dx. Now remember the concept, this is the idea. Okay, next Riemann says that if these two are equal, and equal, of course they are equal, then they must have some equal value. So if A to B fx dx, which is equal to, you know, this is lower sum and sup of P belong to stylish P, you have LPF. If this is equal to A to B fx ds, I mean this is equal to the accurate area, which is also equal to okay, say this is upper integral, which is equal to inf of UPF, where P belong to stylish P, is equal to some A to B fx dx. This is the value, answer of this supremum, and also this is the answer of this infimum, and this is the equal value. When these two are equal, then we say that f is Riemann integrable, and we say that f is, and we write this f belong to R on AB, means that our function is Riemann integrable belong to stylish R on AB. This was the discussion in the last lecture. We have summarized. First, you need to know that function is bounded on closed interval AB. Then you subdivide your given interval into sub-intervals by considering a partition. Then after we are finding upper sums and lower sums to find upper integral and lower integrals. Now since f is bounded, so ultimately function must has supremum and infimum for the entire closed interval as well, right? So since f is bounded on AB, so we let capital M is equal to sup of f of x when x belong to closed interval AB, and similarly small f is equal to inf of f x when a is less than or equal to x except b. You can write like this or you can write like this, no problem. These are the well-known notations. Okay, of course we have then clearly m is the infimum of the entire interval, and this must be less than or equal to mi. You know what is mi? Mi is the infimum of the ith interval. So either this infimum is equal to m or it should be greater than this, because the infimum corresponding to AB is unique. You know that supremum and infimum of a set whenever exist are always unique. That's why either mi corresponding to ith interval, I am talking about m1, m2, m3 and so on, mn corresponding to all intervals, either one of those is equal to m or they are the greater than this. That's why in general m is less equal to capital Mi, and this is always less or equal to capital Mi, where capital Mi is the supremum of your ith interval, and this must be less or equal to n for all I is equal to 1, 2, 3 up to n. Right, you see, if small m is the infimum of your function within the domain AB and capital M is the supremum of your function within the domain AB corresponding to all values, we must have this relation. Small m, this is infimum of the function over the entire interval. So this inf must be less or equal to mi, and since this is the infimum of the ith interval, so this must be less or equal to mi. Equality is possible if function is constant, then supremum and infimum both are equal. That's why in general we can write mi is less or equal to capital Mi, and this must be less or equal to capital M. Okay, now you multiply with respect to delta xi. So this implies m delta xi is less or equal to mi delta xi, which is less or equal to mi delta xi, which is less or equal to m delta xi. Delta xi is positive since xi is greater than xi minus 1 on real line. That's why delta xi is positive. We are taking delta xi is greater than or equal to 0. That's why you can multiply, and so inequality will remain unchanged because you are multiplying by a positive number. Okay. Then add all these numbers. Since this one is the xi minus 1 and this was the xi, and so delta xi was xi minus 1. This was greater than or equal to 0 because you are taking xi minus 1 is less or equal to xi. This was the notation for your partition. You are taking points in the partition which are following this. X naught is less or equal to x1, x naught 1 is less or equal to x2, and so on and so forth. That's why this delta xi, for sake of convenience, for this exam, we are taking greater than or equal to 0. So, by multiplying a positive number, we don't have any problem. Inequality will remains unchanged. Okay. Now you vary I from 1 to n and sum over all these inequalities. Now vary I from 1 to n and add vertically, we get what will happen. This is equal to summation m delta xi, I is from 1 to n, which is of course less or equal to summation mi delta xi, I is from 1 to n, which is less or equal to summation mi delta xi, I is from 1 to n, which would be lesser than which must be less or equal to summation capital M delta xi, I is from 1 to n. So this is say number 1. Now we see that summation delta xi, what is this? I is from 1 to n. This is in fact delta x1 plus delta x2 plus delta x3 plus so on. This is delta xn. Putting the values, we are getting x1 minus x0 plus x2 minus x1 plus x3 minus x2 plus so on plus xn minus 1. You know, this is the telescoping sum. Okay, because if you see with the help of a telescope, you can see that these are cancelled, these are cancelled, these are cancelled, so this will be cancelled with. So that's why we are getting xn minus x0, which is b minus a. Putting in 1, you just substitute the values in equation 1. Okay, we are having so this would be m. First you can write equation 1 as delta xi, I is from 1 to n, which is less or equal to, what is this? This is LPF, and this is less or equal to UPF, and this is less or equal to capital M into summation delta x I is from 1 to n. This means that m into b minus a less or equal to LPF, which is less or equal to UPF, which is less or equal to m into b minus a. What does it mean? That both lower sum and upper sum are lying between two definite values, because you have infimum, this is a number, b minus a, both are the given numbers, it's a definite number, capital M is a definite number. So this means that lower sum and upper sum corresponding to a bounded function lying between this number and this number, this means that both upper and lower sums exist, right? If f is bounded on AB, then upper and then both upper and lower sums exist. Okay, and their sets are in fact the bounded sets. Their sets are the bounded sets. The sets of lower sums and sets of upper sums are in fact the bounded sets. Since they are the bounded sets, that's why you can find their supremum and you can find infimum. Okay, right. This shows that the sets of LPF and UPF for P belong to stylish P corresponding to all partition. You are getting their sets of lower bounds, sets of upper bounds, sets of lower sums, sets of upper sums, or bounded or bounded. Of course, we are saying that when f is bounded on AB closed interval. One thing. And secondly, we will see that upper and lower integrals are also bounded for bounded set, for bounded function, right? So this is in fact the existence of upper and lower sums. Now I want to show the existence of upper and lower integrals. How can we prove that? It's so simple. Now see. Also we know that so m into b minus a is less or equal to LPF, and you know that LPF, this is in fact less or equal to, this is less or equal to sup of P belong to stylish P LPF. Okay, see, this one is a number LPF, and this number is in fact the supremum of numbers of the type. So of course this number must be greater than this. And you know, this is in fact the lower integral. This is equal to lower integral a to b fx dx, and you know the lower integral is always lesser than the upper integral. This is always less or equal to a to b fx dx. And what is this? This is infimum of P belong to stylish P UPF, and you know this is the infimum, must be equal to simple UPF, because this one is corresponding to the partition P, and this is simple upper sum, and this is less than equal to capital M into P. Now you can rewrite this inequality again to see that what we have done. M into B minus A is less than equal to LPF, which is less than equal to A to B fx dx, which is less than equal to A to B fx dx, which is less than equal to, what is this, UPF, and which is less than equal to M into B minus A. Look at this. Consequently, M into B minus A is less than equal to A to B fx dx, which is equal to A to B fx ds, which is less equal to M into B minus A. Again, from here you can see that upper and lower integrals are always also lying between small m to b and minus a into capital M into b minus a. What does it mean? That lower and upper integrals corresponding to a bounded function f on LB or always exist and are bounded as well, right? So this bracket is showing our desired intention, existence of upper and lower integrals. This means that both lower and upper integrals for corresponding to a bounded function f on a closed interval AB are always exist and are in fact bounded as well, because they are lying between the bounds. Okay, so you know that this is the necessary condition, means whenever function is integrable, then f must be bounded. However, if f is a bounded function, then it may not be integrable. I can give you an example to see this one. So remark is, here I have a very elementary remark is number one, if f is if f belong to R, if f belong to stylish R on AB, then f must be bounded on AB. Okay, this is the necessary condition. And secondly, if f is bounded on AB, then f may not be integrable on AB closed interval. So boundedness is not a necessary condition for a function to be as integrable function. However, if a function is integrable, then boundedness is necessary, then f must be bounded. So if a function f is integrable, then f must be bounded. So that's why whenever you want to find the Riemann integrable function, you must have to take a function which is bounded on AB, closed interval. However, if your function is bounded, this is not the case always that your function is Riemann integrable. I am talking about those functions which are Riemann integrable, they must be bounded. Okay, so let's have an example. So here we can understand the concept. So I am taking one example which is a very popular function. You know, this is the Dirichlet function. Okay, if you take Dirichlet function and you take any partition P or F A B, then you will see that your upper sum is giving different values and lower sums are giving different values, so because their infimum and supremum are giving different values. So take function, let fx is equal to 0, say x belong to q, and 1 when x does not belong to q. Whatever you want to take, you can take 0 when it is rational and 1 when x is irrational. So take any partition P on clearly fx mod is less than or equal to 1, so it is bounded on Q, right? So it is bounded in general on R as well. So it is bounded. So since f is bounded on R, so it must be bounded on every its subinterval. And suppose we want to integrate this function f from say that 0 to 1 or whatever from A to B. In general, you want to find integral for this, and you may suppose that delta xi is equal to constant number. Take, assume delta xi is equal to some constant c. You can say this is equal to b minus a by n. Say you are taking n points lying between a and b, so the length of each interval, if you want to find n intervals, so length of each interval would be b minus a by n, right? You take length of the entire interval ab, and if you divide by n, this means that you are taking n subintervals, so you have n plus 1 points in your partition, right? And suppose you are taking points from x0 to x1 with a constant distance. Say this is c, means that the partition you are taking x0 to x1, this is c, then x2, this is c, then x3, this is C, and so on, and xn, and this one is xn minus 1. This interval is also C, right? For sake of convenience, because we want to have a counter example against the concept, that's why you are free to choose any interval, any partition, and any example. No problem. We want to give an example against generalization of the concept, right? So, if you see that, assume mi, and here mi would be equal to 1 for all I, and small mi would be equal to 0 for all I. Because your function is 0 when x belongs to Q and 1 when x does not belong to Q. So corresponding to every subinterval, you have infinite numbers which are rational, and you have infinite numbers which are irrational. Suppose you are taking 0 to 1 interval. I want to integrate from 3 to 9, and I have taken this subinterval 3 to 4, and between 3 to 4 there may be many, there are in fact many points, infinite points, infinite rational numbers, and in this subinterval you are getting infinite irrational numbers as well. You know the density theorem. Density theorem says that between two real numbers there always exist infinite rational numbers, and between two real numbers there always exists infinite irrational numbers. So the supremum, since you are having values 0 and 1, so that's why corresponding to every subinterval the minimum value would be the 0. So capital Mi corresponding to every interval, because every interval is containing an irrational number, surely. So Mi should be 1, and small mi is equal to 0 for all I, whatever the interval you are choosing. So that's why summation mi delta xi is equal to, in fact, summation 1 into delta xi, I will from 1 to n, and this is equal to, what is delta xi? Delta xi is c, and this is summation I varies from 1 to n, this is c, I varies from 1 to n, okay, and what is this? This is in fact okay, this is nc, say this is nc, no problem. N is your constant, and you know that if you add c time I is from 1 to 2, this is equal to c plus c, this is 2c, and if you add c is any constant number, I is from 1 to 3, this would be equal to c plus c plus c, and since we are adding from 1 to n, that's why this must be nc, this is nc, okay. So if I want to find what is this? This is in fact UPF, and if I want to find inf of UPF, P belongs to stylish P, this is in fact inf of NC type number, right? And you know n and c both are constant. This must be equal to, where P belongs to stylish P, this is equal to NC, right? Suppose we are also fixing one thing, is that in every partition you are taking endpoints. That's why with the understanding that the distance between two points is same, I mean that the length of every subinterval is c, in fact. That's why this is nc, a constant number. So the lower integral is your lower integral from a to b fx dx is equal to nc, right? Similarly, you can find upper integral. For upper integral, sorry, this is your upper integral. This is your upper integral. This is your upper integral. For lower integral, since mi is equal to 0 for all I, so summation mi delta xi is equal to 0 into c, which is 0. So that's why 0. So if you take soup, this was the lower sum LPF, and if you take supremum over all partition, this implies soup of P belong to stylish P, LPF is this is also of course soup of P belong to stylish P of 0. This is equal to 0 because it is the constant as well. Hence this means that and what was this? This was the a to b lower integral fx dx. Hence a to b fx dx, which is equal to, is not equal to a to b fx dx. This implies that f does not belong to stylish R on AB, where AB was any interval, right? So in this way, you can see that corresponding to this interval AB, our function which was bounded on a given set, so because it was bounded on every subinterval as well, so you can find supremum and infimum corresponding to every subinterval. Okay. However, we have seen that we have different upper sums and lower sums, so because function is not integrable, because we have the definition f belong to R alpha if and only if its lower integral and upper integral both are equal and equal to the their equal value, whatever it is. You can also have the general idea is, if you take lower sum like this LPF, instead of writing H or something else, you can write like this: LPF is equal to summation mi delta xi, and since this is equal to 0, 0 delta xi, which is equal to summation 0, this is 0, yes. And secondly, since mi is equal to 0 for all I, and secondly you can write UPF as, this is summation capital Mi delta xi, summation delta xi 1, because you know corresponding to every I, mi is equal to 1, since mi is equal to 1 for all I, that's why this is equal to b minus a. Again you have a constant number. You know summation delta xi I is from 1 to n is equal to b minus a. If you are not liking the idea of taking some number nc, that was nc, and here you can write directly from this is I is from 1 to n, you know this is equal to b minus a, and then take infimum from P belong to stylish P, UPF, this is equal to in fact infimum of P belong to stylish P, this is b minus a, and since b minus a is constant, this is equal to b minus a. So NC was b minus a in fact. Okay. Since and this is the your upper integral, it will be fx dx, and this was the this implies soup of LPF. We already have calculated this one as 0, which was your a to b fx dx. Hence, you have seen that its lower integral is 0, while its upper integral is b minus a. You know, you have values of b and a. If it is 2 to 4, then this is 2. If you have 2 to 9, then this is 7. Whatever it is a constant number. So you have seen that lower and upper integrals are different, even though the function was bounded. So that's why if a function is a bounded function on an interval a to b, then this is not always the case that function is Riemann integrable, unless the necessary condition is its lower integral and upper integral both are equal. Similarly, you have another simple example is can you find integral over line of x-axis? Integral over line of x-axis are you can say this is, you know, line of x-axis is y is equal to 0. So here function y is equal to fx, this is equal to 0. This implies mi is equal to capital Mi is equal to 0 for all I. So this implies summation mi delta xi is equal to summation capital Mi delta xi is equal to 0. So this implies lower integral a to b fx dx, which is equal to upper integral a to b fx dx, which is equal to 0. That's why if you integrate directly from a to b 0 dx, this is equal to 0 into a to b 1 dx, this is equal to 0 into c, this is equal to 0. So we can verify that if you integrate this function, line of x-axis, you are taking function as line of x-axis, and you are taking line of x-axis is y is equal to 0. You are taking function of fx is equal to 0. So that's why you can have a theorem as well, that if fx is equal to 0, if and only if its lower integral and upper integral both are 0, and conversely, if upper and lower integrals both are 0, then you have only one choice, that function is 0. Okay. Next, we can apply the idea on some other examples. Can you integrate fx is equal to, can you integrate fx is equal to x, fx is equal to x square, fx is equal to constant c, you take any constant c, fx is equal to x cube, and so on, fx is equal to xn, where n belongs to natural. You can integrate all these functions over a closed interval ab. So I want to calculate one of c and one is x square, and rest of functions similarly you can calculate. So if fx is equal to c, if function is equal to c, then of course, then corresponding to every p of ab, okay, you want to integrate this function, constant function, over a closed interval ab, then corresponding to every partial p of ab, you have mi is equal to 0, c, and which is equal to capital Mi as well. Since function is constant, so we are not changing the values. That's why all soups corresponding to subintervals must be c, and all imps corresponding to every interval must be c as well. So the lower integral is summation mi delta xi, I will from 1 to n, would be equal to summation capital Mi delta xi, I will from 1 to n, would be equal to summation c time delta xi, I values from 1 to n, would be equal to c times b minus a. So this means that lower integral, since this is a constant number c into b minus a, that's why if you vary partition p over of the interval ab and take supremum over all lower sums or infimum over all upper sum, you will get the same number because it is a constant number. So because a to b fx dx lower integral and a to b fx dx upper integral would be equal to b into c b minus a, which is in fact the a to b c dx, right? Hence this function is Riemann integrable on your closed interval ab. Next, I can find function fx is equal to x square is also integrable on a closed interval ab. See how we can solve this as well. Okay, function fx is equal to x square and interval is ab. Again, you need to find supremum corresponding to every subinterval and infimum corresponding to every subinterval. So take a partition P, take P is equal to, you can choose any partition P of AB, right? This is equal to, in fact, if we can fix instead of A from 0, we have little easier solutions. Then you can generalize this 0 with A. You write A and solve again this. It would be so simple. It would not be difficult. So for sake of convenience, I am choosing 0 instead of A. Okay. So you take a partition 0, then you can have a partition. Take say C by n, then 2C by n, then so on, then lastly NC by b minus 0 is n. Take this is b, not c. This is b by n, because here the length of 0 to b is b, and I want to b minus 0. And if I divide this length by n, this is b by n. So b by n is your constant value, because I want to keep a constant distance between any two points of the partition AB, so that the length of your subintervals remains constant. Okay, so this is the idea. Last could be your last is NB by B. So the partition is 0 B by n, 2B by n, and so on is B, right? Okay, one thing is also notable, that this function is increasing on this interval 0 to b. That's why this is an increasing function on its every subinterval, and so because corresponding to every ending point you are getting maximum value, and corresponding to first point you are getting infimum value. So note that f is increasing on 0b, therefore mi would be equal to f of xi for all I, and small mi would be equal to f of xi minus 1 for all I. Because your function is like this, your function is increasing, So that's why your function this is your increasing function, and it's your xi minus 1 value xi. So this number is in fact mi corresponding to this, and this number would be mi, and this is happening corresponding to all values of I. I values from 1 to 3, I values from 1 to 2 and so on up to n, 1, 2 and so on up to n. Yes, so corresponding to every subinterval, the maximum value is at the ending point, and the minimum value or infimum is in fact at the starting point. Okay, so now we can find lower and upper sums easily. Remember the partition. So what is happening here? Your upper sum is UPF would be equal to M1 delta X1 plus M2 delta X2 plus so on Mn delta Xn. Remember the partition. Partition was 0, B by N, 2B by N and so on. Last is B. What is the difference between these two? This is your difference, is B by N minus 0. This is B by N. Difference between these two is 2B by N minus B by N. This is again B by N. So B by N is the constant distance between any 2 points. Is the constant length of all subintervals, because we have assumed that delta xi is constant. We have assumed delta xi as b minus a by n, and your a was 0, so b minus 0 by n, so this was b by n for all I. This was the length of every subinterval. So this is equal to, what is m1? m1 is in fact fx1. The first interval is your first interval x0 x1. Since function is increasing, so at x1 you are getting the maximum value. Second interval is x1 x2. So since function is increasing, you are getting maximum value at x2, right? And so on and so forth. This is fx1. What is delta x1? Delta x1 is b by n plus fx2 b by 2 plus so on b by n fxn b by n. And what is this now? This is equal to b by n is constant, and inside you are getting f of xi. I will sum 1 to n. What is f of xi? Xi is your function was what was your function? Function was x square. This was the function x square. So fxi, the maximum value is at corresponding to this. So in first order, this is b square by n square. Okay, I think we should write separately. B by n into fx1 plus fx2 plus so on plus fxn. Now what is this? B by n into, what is fx1? Add this number. This is b square by n square. This is b square by n square plus, second one is 2 square b square by n square. This is 2 square b square by n square, and plus so on, plus lastly this is b square. Okay, or you can say that n square b square by n square, we can multiply and divide by n square. Okay, now you can take b square by n square common to each. You are getting b by n into b square by n square. Inside you are getting 1 square plus 2 square plus 1 plus n square. And what is this? Everybody know b by n into b square by n square. This is n into n plus 1 into 2n plus 1 divided by 6. Yes, we can further simplify this. This is equal to b cube by 6, and I can write these are cancelled. This can be written as 1 plus 1 over n, and this can be written as 2 plus 1 over n. What is this? This was UPF. Okay. Now you can have infimum over all partitions. If you take infimum over all partitions, then infimum of P belong to stylish P, UPF would be equal to, in fact, infimum of P belong to stylish P, B cube by n by 6 into 1 plus 1 over n into 2 plus 1 over n. Yes, this is the right answer. Okay, now again think on this. If you are taking infimum over all this, infimum of UPF, where P belong to stylish P, what would be equal to? This is equal to, and what is this? This is our upper integral a to b x squared dx is equal to infimum of P belong to stylish P. Inside is b cube by 6 into 1 plus 1 over n into 2 plus 1 over n. Right. Now you see that when you are taking infimum and you vary n is in fact the number of points. If you increase the number of points, this value ultimately is going to be is decreasing, in fact. And for larger values, you can have very large values, but the partition is finite. Even in a finite partition, you may have many large values, and corresponding to those values, 1 over n and 2 plus 1 over n is identically 0, or will contribute no bigger value in the answer. So it's and you know b cube and 6, these are the constant numbers. So answer would be b cube by 6 into 1 into 2, right? So the answer would be equal to b cube by 3. This is your lower integral, upper integral. Similarly, we can find lower integral, and you know that since function is increasing, so now every inf would be at the first value. Now again, if you write the formula for low sums, what would happen? LPF would be equal to m1 delta x1 plus m2 delta x2 plus 1 mn delta xn. This is equal to, again, delta x1 delta x2 delta xn all are same. Delta xi is equal to b by n for all I. So this is equal to, what is m1? m1 is in fact first time it is 0, and this one is b by n, plus this time this is f of x1, this is f of x0 to x1, then you know this is your x naught is equal to 0, and which is less than x1, which is less than x2, so on, less than xn minus 1, which is less than xn, are equal to, you can insert no problem, which is equal to b. So for the first time you have infimum at 0 for this interval, and for this interval you have infimum at x1. This is equal to fx1 into b by n plus b by n into fx2 plus so on. In last interval this would be at xn minus 1, because function is increasing, so the infimum value would be at the first point. So plus lastly you are getting b by n into f of xn minus 1, right? This would be the answer. So now what is the answer is, again remember, you recall your partition. What was the partition? Partition was b by n, 2b by n, 3b by n, and so on. Last was b, which is n, b by n, and the last one was n minus 1 into b by n. This is the last inf of your last interval, right? So answer is, this is 0, 0 into b by n, plus this one is b square by n into b by n, plus so on. Last would be b by n into this one, b into n minus 1 by n whole square. Okay. Again, you can have b by n common to all, and inside you are getting 0, 1 square. Also if you take b square by n square, also b square by n square, this is square, this is square, b square by n square, and this is b by n, would be equal to 1 square plus 2 square plus so on, plus n minus 1 square. So what is the answer is b cube by n into n square, and you know this is equal to n into n minus 1 into 2 into n minus 1 minus 1 divided by 6. We know this formula from 1 square, 2 square to up to n minus 1 square is equal to n into n plus 1, n into n plus 1. This is in fact the formula is n minus 1 into n minus 1 plus 1, which is n, into 2 into n minus 1 plus 1 divided by 6. So what is this? B cube by n into n square into this one is n minus 1 n, and what is this? 2n minus 1 plus 1. This is 2n minus 1 divided by 6. Yes, these are cancelled again. What remains inside? So LPF is equal to b cube by n square, and you can write like this, b cube by 6. This further can be written as 1 minus 1 over n into 2 minus 1 over n. Again, if you take supremum, then again by varying the partition corresponding to all partition, this value would be 0, tends to 0, and this value is also tends to 0, because you can have very large natural number corresponding to a finite partition. You are taking a finite partition with very large numbers, so corresponding those numbers 1 over n is identically 0, right? So that's why if you take sup of p of f, p belong to stylish p this is equal to, in fact, a to b lower integral a to b fx x square dx. Sorry, this is x square dx would be equal to b cube by 6 into 1 into 2, which is equal to b cube by 3. So, since lower and upper integrals are equal and equal to b cube by 3, that's why you have the answer that this is Riemann integrable. So, here a to b x square dx is equal to a to b x square dx is equal to, sorry, from 0 to b. You are taking from 0 to b. This is also from 0 to b. We are discussing from 0 to b is equal to b cube by 3, which is in fact 0 to b x square dx. Yes, this is x cube by 3 and b cube by 3. The answer is true. Hence, we know that fx, which was x square, so is Riemann integrable on 0b. That is, f belong to stylish R on 0b. Okay, I have completed this example, and then the rest of the example for fx is equal to x cube, and for fx is equal to x, or for fx is equal to any polynomial xn, you can complete that these monomials are in fact Riemann integrable over your closed interval ab, and also you can choose some a instead of 0. You can generalize, you have to see some formulas a plus b square like this, and you have to simplify your answer. So these are very simple examples, and with the help of Riemann integral we can find their lower integrals and upper integrals, and we are having that both are equal. That's why these all functions are Riemann integrable on closed interval a to b, because these all are in fact bounded on closed interval a to b. Okay, so with this I want to finish my lecture. Try to revise lecture 1, and then try to solve all exercises in lecture 2. Okay, thank you very much. Allah Hafiz.